If you've been struggling to solve this tricky integral, I'm about to show you how to understand it and solve it in just a few minutes. And if you want to crush that AP exam for when you see problems like this, be sure to ninja kick that subscribe button and strap in because the dojo is about to get started. We have this definite integral from negative pi over 2 to pi over 2 of the absolute value of sine of x dx. Now, the absolute value here is crucial to understand because it changes how we solve this problem. It's not going to be the same as if you just had sine of x dx. What I like to do here, and you can leave a comment in case you took a different approach, is I'm using the unit circle here and I'm working with radians. So I know I called the variable x above, but bear with me because here I'm going to use theta instead. And I want to look at both pi over 2 and negative pi over 2. Now, if you remember, those are going to be 90 degrees and negative 90 degrees respectively, because in degrees, those radian values are basically going to be at both ends of the y-axis. And so because we have a sine of x function that has an absolute value, this is usually a hint that you want to use a piecewise function approach where you're breaking up the domain of the problem into parts based on the positivity or negativity of x, or theta in this case. So what I'm going to do is I'm going to start with the upper half of the definite integral. So we'll go from a 0 value to positive pi over 2. And you'll notice that on the Cartesian plane here, when working with radians, sine of theta will always be greater than or equal to 0 because we are above the x-axis. So your y component, if you were to make a triangle here, is always going to be non-negative. Now, what this means is that because we have an absolute value of sine of theta here, when you have a positive result for sine of theta, the absolute value isn't really doing anything. So in other words, for this part of the domain, we can just simply say that the absolute value of sine of theta equals sine of theta. We'll just drop the absolute value. Okay, now for the negative part we're working with, this negative pi over 2 to 0, now we're going in the opposite direction, which is going to be clockwise. We're going from 0 to negative pi over 2, and we're basically going underneath the x-axis. And so you'll notice that sine of theta is going to be negative in this case, other than, of course, at 0. And so now if you have sine of theta being negative, but we have an absolute value in the original problem, you're changing a negative to a positive. So that's basically saying that the absolute value of sine of theta is kind of like a -1 times the result of sine of theta to make the result positive. Now, here's a quiz question for you. Is this all correct at an angle of 0? Why or why not? And the hint here is the inequality that we're using. Okay, so now going back to the original problem, negative pi over 2 to pi over 2 of the absolute value of sine of x dx, what I can do is just taking the piecewise approach, we're going to actually break this up into two parts. Remember that when you have a definite integral, you're talking about the area under a curve. So we're basically partitioning or breaking up that area into two parts, and we're just adding the areas to get the final answer. So I'm going to break this up into two integrals, one that has the negative angle part and one that has the positive angle part. And of course, 0 is non-negative as kind of that edge case. And going back to my original question for you, why are we able to break it up this way, with the value of 0 in particular being at an endpoint of each of these integrals? Can you tell me why? So that's a very important question to ask. But basically, if you already observed, continuity matters here. For the original function, we have continuity at x equals 0, and that's why we're able to basically do this. And so, okay, now we're going to work with that negative pi over 2 to 0 integral for negative sine of x dx plus the integral from 0 to pi over 2 of sine of x dx. And those are just me bringing down what we did above, right? For those different regions, we dropped the absolute value and we just simply worked with two parts of the unit circle. Okay, now for the left-hand side, we have a negative sine of x dx. I'm just going to bring the negative out of the integral to just make sure I don't goof up my signs at the end of solving the problem. Because remember, we can just distribute that constant out as a -1. And I'll leave the right-hand side the same. Now, if you remember, the integral of sine of x dx is negative cosine of x plus c. But here I'm not showing that plus c. Do you remember why? Okay, so we're going to evaluate the different integral answers here using the limits of integrals. So from negative pi over 2 to 0 and from 0 to pi over 2. And so you're going to find that on the left-hand side, you're going to have this negative, which becomes a positive, right? So when you distribute that through, you'll get cosine of 0 minus the cosine of negative pi over 2, plus in parentheses, just making sure order of operations are correct, the negative cosine of pi over 2 minus, and then in parentheses, negative cosine of 0. And when you simplify everything, you're going to find that you get 1 minus 0 plus negative 0 plus 1, which is 2.